that hopefully should just be foundational. Actually, before I reach here, just to understand the crowd, how many of us already know the answers to these questions? Read it through some of these questions, just to see, how many of the people are from the existing cohorts already know a bunch of these things. Which, if you are using Bitcoin, or if you have used Ethereum or Solana, some of the questions that you might get. If you don't understand the question, or if you don't know the answer, then select no. Otherwise, select yes. A few questions are. Why would a person start a new cryptocurrency miner? Why should I start a miner today? What reward do I exactly get? How do I get the reward? How do forks get resolved? What are forks in a blockchain? Can transactions be reversed in a blockchain? If they can be reversed, what is the solution around it? Because if I pay someone 2 BTC and he gives me some gold, and then the transaction reverse, then I have my 2 BTC back, I also have his gold. That's a problem. Can a miner move money from one random address to another? I mean, of course the answer is no, but how that happens computationally or mathematically, do you already know the answers to these questions? Are these easy questions? Have you already seen these questions before and explored their answers, yes or no? Just to get a sense of how many of us understand blockchains already. Okay, so 85% say no, and 15% say yes. That's a 20-80 now. 21-80, that's good. 22-78, cool, I get a decent idea. I think for 22%, all of this should also be fairly easy. And all of these topics are not generally covered in full stack. You don't need a bunch of these cryptography, not cryptocurrency, but cryptography concepts. In general, full stacky stuff, but if you're a CS student, you've probably done them. So we'll kick things off with bits and bytes. All of these have nothing to do with Bitcoin or cryptocurrencies. They are CS topics that predate the creation of Bitcoin, and something you should probably generally know in respective of crypto. We'll kick things off with bits and bytes. Some of you might already know this. For everyone else, if you have a computer that looks like a Mac machine, the Mac machine actually has a few components in it. There is something called RAM, or random access memory. There is something called SSD, where you store your data. You might have 256 GB SSD, or 512 GB SSD. And RAM, you usually have 8 GB, 16 GB. It's a little more expensive to buy RAM compared to SSD, because RAM is much faster to what RAM is and what SSDs will come to, but it's basically memory. If I'm storing a video in my computer, it gets stored over here. So if I have a 1 GB video on my machine, that 1 GB video is stored in this, some part of this 256 GB SSD. If I have a game that's 20 GB, so that 20 GB game is also stored over here. When I run that game, or when I run that video, then that video sort of gets loaded over here, some portion of it. When I'm playing a game, the visualization that I'm seeing as I'm moving aage piche and something is happening, then some part of this game, some program of this game sort of moves to the RAM, and that is your program in execution. Jab aap program ko run karte ho, even if you run something like node index.js, or go run, or cargo run. If you're running a Rust program, a JavaScript program, you're opening the browser, then some part of your RAM is being occupied by these programs. If some of these programs is extremely memory heavy, for example, let's say you have a program that converts video from MP4 to AVI, and the program is written a little unoptimally, such that it loads the full video in memory first, and then converts it to a different format. Then that program might not run. It might run out of memory, because that specific program might need to take this, let's say 10 GB video or 20 GB video, and load that here in RAM. But since you only have 8 GB of RAM, you'll see an out of memory error over here or something like that. So these are the high level components. Then there's the CPU, there's the GPU, so on and so forth. These are the high level components of your machine. But hopefully you understand these components are physical things, right? It's some board. If you've seen a motherboard, if you've seen a RAM, it looks like some spiky thing, which effectively only stores two states. It has, when we say 8 GB, or when we say 16 GB, what we mean is that there are a lot of small switches on this RAM. And these switches can have one of two states. They can either be on or they can be off. That means this switch can either be a 1 or this switch can either be a 0. This switch can either be a 1 or it can be a 0. These physical hardware things that you put on your RAM that exist inside your MacBook are basically a bunch of small transistors, a bunch of small switches that can have one of two states, on or off, 0 or 1. When I am running a game where a lot of visualization is happening, there's a person moving in 3D, what is happening is RAM में बहुत सारा data चलना चाहिए. Where is this person standing? Let's say I start a GTA game on my Mac machine. So on my display, I'm seeing, whatever, a tree over here and then a person, slightly fat and dysmorphed person. This person might be standing at, whatever, X20, Y30, Z200 in that specific physical space. So these numbers need to be stored in this, RAM in the form of zeros and ones, because your RAM doesn't understand 20. It doesn't understand physical space when there is a tree over here. It only understands 0, 1. So you have to figure out how to store this number 2 in this RAM in the form of zeros and ones, 30 in the RAM in the form of zeros and ones, so on and so forth. This is called the binary representation of just a number for now. Even strings ho gayi, booleans ho gaye, whatever data types you might have seen in JavaScript, Golang, Java, Rust, are all eventually converted to what's called a binary format. Why binary? 0, 1, there are only two states it can have. And let's start off with numbers, but even strings, even the trees over here are basically a bunch of points, right? A 3D tree is nothing but a bunch of points and how they're connected. It's a bunch of triangles. If you connect a bunch of triangles, you can see a 3-dimensional tree, right? All of these are just numbers or strings or, things that you and I can read. For example, my name is Harkirat Singh, a string like this, need to be converted into zeros and ones. How they get converted is based on, certain what are called encodings. I repeat, certain encodings. आप encode कर रहे हो 20 को in form of some zeros and ones, 30 को in the form of some zeros and ones. My name is Harkirat ko in the form of some zeros and ones. This conversion we need to understand. Okay, what are these various encoding formats? How can you encode a number to a binary to a number, a string to a binary back to a string? That's what we need to understand in this section. Why? Because eventually when we do cryptography or cryptocurrencies, we will need a bunch of these, converting strings to bytes or numbers to bytes, bytes to numbers, so on and so forth, especially when we are writing smart contracts or dealing with public and private keys. तो हमें ये थोड़ा सा समझना पड़ेगा कि how encodings work and how data is actually stored in your RAM, because how it is stored in your RAM is how it is stored in various miners also all around the world. When I say miner, I mean a Bitcoin miner किसी ने अगर चालू कर रखा है. That's how you send data to them through bytes and bits, and they sort of respond, let's say, in also bytes and bits. So what do we need to understand? To kick things off, we need to understand what are bits and bytes. Then we'll understand how data is encoded to bits and how bits are converted back to data. What is a bit? A bit is the smallest unit of data in a computer that can have one of two values, 0 or 1. Think of it like a light switch that can either go on or go off. Any data on your machine, any MP4 file that's stored on the SSD is stored in the form of binary or zeros and ones. What is a byte? A byte is a group of 8 bits. 8 bits को एक साथ लोगे, उसको एक byte बुलाया जाता है. Why 8? Just a random number some person chose, and today that is why we have 256 GB and not 300 GB RAM. Because unfortunately we deal in terms of bytes, and bytes are a multiple of 2 and not a multiple of 10. It would have been nice if it would have been a multiple of 10. If a byte was a multiple of 10, it isn't. 8 bits equal to 1 byte, and hence we have 256 GB, 512 GB, and not round numbers like 500, 250, so on and so forth. A byte is a group of 8 bits. It's a standard unit of data used to represent a single character in memory. It is the standard unit of data used to represent a single character in memory. A, B, C, D. If you want to store A, the character, finally in memory, can you store it in a single bit? A bit can only have two states, 0 or 1. If you want to store a boolean in memory, it can be either 0 or 1. It can be stored in a bit. If you want to store a boolean in memory, something that can only have a state of true or false, then yes, you can say if this specific switch is off, that means it is false. If it is on, then it is true. Something like this. But can you store a character A, B, C, something like this in 1 bit? Unfortunately not. And the standard encodings that exist, ASCII, UTF-8, store it in 1 byte, 3 bytes, 4 bytes. We'll come to what that is, but that's the general idea behind the conversion between bits and bytes. You can store data in 1 bit. You can only store either 0 or 1. But if you have a byte, that means if you have 8, 4, 5, 6, 7, 8. If you have 8 bits, you can actually store a lot more data in it. How, we will see very soon. We first need to understand binary conversion before we understand how much data you can store in a byte. But what is a byte? So it's a combination of 8 bits. Okay. First conversion that we need to understand is the conversion of numbers to decimal. I hope some of you already know this, but if you take any number, let's say 100, it can be converted into a bunch of zeros and ones. And the way it is done is slightly more mathematical, but hopefully very digestible. So let's start with a few examples. If I want to store 0 in binary, its binary representation is actually 0. If I want to store 1 in binary, its binary representation is 1. If I want to store 2 in memory, its binary representation is 1, 0. If I want to store 3 in memory, its binary representation is 1, 1. Can you guess what the binary representation of 4 would be? It's 1, 0, 0. Of 5 would be, it's 1, 0, 1. Of 6 would be, it's 1, 1, 0. From pattern matching, you can probably understand what is happening, how I went from 0 to 1, 1 to 2, 2 to 3. But mathematically also, the binary representation basically is, okay, take the last bit over here, 0, multiply it by 2 to the power 0. Plus, take the second last bit over here, 1, and multiply it by 2 to the power 1. And take the third last bit over here, 1, and multiply it by 2 to the power 2. 0 into 2 to the power 0, 1 into 2 to the power 1, 1 into 2 to the power 2 is equal to 6. That is how you convert decimal to binary, binary to decimal. How do you convert a number from decimal to binary? By somehow, reaching this formula. Now, there are ways how you can reach this formula. Very laggy video. Very laggy video, guys. We take a small pause. Now it's okay, someone said. We wait for a bit, 1 minute breather. Hello, hello, mic testing, mic testing. Are we good now? Yes or no? Alrighty. I will proceed. Mikey, call me again if it becomes problematic. What I was saying was, to convert a number to binary, there is a formula. Like hopefully some of you have, this is a common lead code question that you will find, which is given a number where a equal to whatever, something like this. How do you convert it to binary? The way it is done is slightly mathematical. You take the number, let's say the number is 301, you modulo it with the 2, and whatever you get is the last bit, which is 1. Then you divide the number by 2 and then take its floor, so it becomes 150. Then you take a modulo with 2 again, and that's 0. So that's going to be the pre-final bit, and then you divide it by 2 again, so that's 75. You take a modulo with the 2, and that becomes 1, so that's going to be the third last bit. Then you divide it by 2, that becomes 37. You modulo it by 2, it's again 1, so the fourth bit is going to be 1, so on and so forth. There's a very standard, if you think of it a little, you'll understand. Hopefully converting binary to number is easy. Take the last bit, multiply it by 2 to the power 0. Take the second last bit, multiply it by 2 to the power 1. Take the third last bit, multiply it by 2 to the power 2. Take the fourth last bit 0, multiply it by 2 to the power 3. take this bit multiplied by 2 raised to the power 4. That's how you convert a given binary number to decimal. Decimal to binary कैसे होता है? You take a modulo with 2, that's the last bit. You divide it by 2. Take the floor. For example, dividing 301 by 2 is going to be 155.5. You take its floor, that's 150. You again take a remainder with 2, it's 0. That's the second last bit, so on and so forth. That's how you convert every decimal number to binary, binary number to decimal. So if it's just numbers we are dealing with, if every program out there was just numbers, then this is how you would, store data finally in your RAM in the form of zeros and ones. You'd probably decide a specific size कि यार हमारे केस में numbers can only be as big as 2 raised to the power 32. If you've ever solved C++ में DSA problems, you might know the concept of long. You might know कि ints are 32 bit and longs are 64 bits. So if you've done comparative programming, then probably you've dealt with longs. And generally when you store numbers, they're either stored in the form of 32 bits or in the form of 64 bits. 32 bits is, basically means you can store a number from minus 10 to the power 9 to somewhere around, 10 to the power 9. And 64 bits means you can store a number somewhere around minus 10 to the power 18 to plus 10 to the power 18. That's the high level. Maybe there are, some nuances on how numbers are stored, how negative numbers are stored. The last bit in a 32-bit number, the last bit represents, if it's 0, it means it's a positive number. If it's 1, it means it's a negative number or something like that. So if you've ever, क्या होता है C++, there are 2 ways you can create ints, and one int is only positive. I forgot what it is called in C++. Someone can know. Refresh my memory. All competitive programming people already know this. But there is a way to only create positive numbers in C++. What is it called? Signed numbers. Yeah, signed and unsigned numbers. So if you want to store a lot of positive numbers in C++, then you write some unsigned int a. Now this can be much longer because now you're only storing positive numbers. So all the bytes that you have 32 bits. All 32 bits can now store more about the number. The last bit can also store 0 or 1. Versus if it is a signed integer, then the last bit stores whether it's a negative number or the positive number, and everything else stores the normal binary representation. इसमें भी ऐसा होता है कि what does 10000 and 0000 mean? A negative 0 and a positive 0 are the same thing, right? So that is why negative side पे एक extra हो जाता है, वो -1 बन जाता है, positive side पे +1 बन जाता है. One of these two happens, and that is why if you have an unsigned int that's like a normal int in C++, it can go from minus some number x -1 up to x. So negative side पे एक number कम होता है या whatever +1, because you take one of these two numbers as the last number over here. तो negative में आप थोड़ा ज़्यादा store कर सकते हो या positive में आप थोड़ा ज़्यादा store कर सकते हो. But generally numbers कितने bits के होते हैं? In most languages they are 32 bits. Generally when you are storing a number over here, you are taking 32 of these bits or 4 bytes and storing a number, irrespective of if it's a very small number. For example, 20 is a very small number. 20 की binary representation would be something like this, 11000, I think. But it's stored like this in 32 bits with a lot of zeros, and then 11000. Same is true for 300, 400, 500. When you're storing integers, most languages take 32 bits and then store an integer. If you use long in C++, then you take 64 bits and store an integer. Hopefully, that tells you how numbers are stored in the form of bits and bytes in computers. Let's do a poll. Do we understand bits and bytes and how numbers are stored in the machine eventually in the in your RAM, in your SSD? How do you convert a decimal to binary, binary to decimal? There are a bunch of converters that you can use. Decimal to binary converter. You can just go over here and try to convert a decimal number to binary, binary to decimal. If you don't want to do the math, or there's a lead code question, you can code it yourself. Seems like most people understand. But if you do want, select a number, and this is the binary representation of this number. And then if I take a much smaller number, 33, then this is the binary representation of 33. And this is how it's written. Okay, 33 with to the base 10, which is like a decimal representation, is equivalent to 100001 in the second base, or as a binary representation. Next question: how do you store strings? If I want to write something like my name is Harkirat, how is this stored in the form of binary? And what is the binary representation of M, for example? What is the binary representation of Y? What is the binary representation of space? So on and so forth. So here come the concept of various types of encodings. There are not just English characters. Agar sirf English characters hote, if all we had to store was A to Z, and then A to capital Z, let's say, and some special characters like this, let me see, some special characters, and then of course numbers from 1 to 0 to 9. In the end यही स्टोर करना होता. Then we could have said something like this कि यार अगर string स्टोर हो रही है तो the binary representation of A is going to be 0, B is going to be 1, C is going to be 2, D is going to be 3, E is going to be 4. करते करते capital A is going to be 27, capital B is going to be 28. करते करते 0 is going to be whatever 54, and then 1 is going to be 55, and then karte karte question mark is going to be some 64, 65, so on and so forth. We can write our own language representation kya lo कि यार A's binary representation is going to be this, B's binary representation is going to be this. You might ask, Harkirat, how do we know कि ये number है या फिर string है फिर? How do I know if something that is stored in RAM over here, if it is a number or if it is a string? So what happens is, in actuality, in memory, the type is also stored somewhere here. Here the next thing is going to be a number or a string or whatever, a boolean to nahi, but you get the idea. The type is also stored in a bit, or let's say 2 bits or 4 bits, and then the actual thing is stored right after. Whenever you're encoding and decoding, serializing and deserializing to bytes, based on your हमारा तरीका ये है, मान लो कि I have written my own language compiler कि यार मेरी language में तो एक ही representation ये है. I have written my own encoding. I'm going to call it Harkirat encoding. मेरी language में the only alphabets that are supported are A to Z, capital A to capital Z, 0 to 9, and some special characters. So in my language, this is how I'm going to encode 0, A, B, C, D, and then this is how I'm going to encode 1, 0, 2, 3, 4, 5, 6, 7, like that. But of course, there are standards that already exist for characters. Ki how should H be represented in binary? How should A be represented in binary? You might have already heard of ASCII or UTF-8. There are 2 ways you can encode strings, but there are actually many encodings that exist. इनको क्या बुलाया जाता है? These are called encodings. This is Harkirat encoding. In my encoding, A represents the 0th byte, B represents the 1th byte, so on and so forth. But in more standard encodings like UTF-8 or ASCII, A represents something, B represents something. So let's look at some of these encodings. Bytes are cool but highly unreadable. Imagine telling someone my name is 0011010, something like that. It's easier to encode data so that it becomes more human readable. Some common encodings include ASCII, hex, base 64 and base 58. Even UTF-8 is a popular one. ASCII, hex, base 64, base 58 and UTF-8. Let's understand all of these. Let's start off with ASCII. ये सबसे कॉमन वाली है जो आपको और मेरे को समझ आती है. Whenever you are writing English, if I open my network tab over here and if I write where A equal to Harkirat, then the encoding in which it is stored is ASCII. तो इसमें कुछ होता है A.to char to string, I forgot. There is like a function you can call to see कि ये actual में binary में कैसे represented है. To see what is the H की binary representation क्या है, B की binary representation क्या है, what is that number that translates to this. ये थोड़ा confusing हुआ होगा. My bad. What I meant here was this: 01, 11, 100, 101, 110, so on and so forth. Okay, in my Harkirat encoding, A will be represented as 0, B will be represented as 1, C will be represented as 01, D will be represented as 11, E will be represented as 110, so on and so forth. In ASCII, one character is 7 bits. तो ASCII वालों ने कह दिया कि यार हम ASCII वाले हैं, we support a few characters, for example A to Z, a to capital Z, and bunch of these special characters, and then every number from 0 to 9, a bunch of other extra characters, and each one of our characters will hold up 7 bits, will take 7 bits. So 4, 5, 6, 7. So 0, 0, 0, 0, 0, 0, 0 would represent something. Let's say, it represents A. Let's say. And then 0, 0, 0, 0, 0, 0, 1 would represent something, so on and so forth. In actuality, it looks something like this. In ASCII, exclamation is 33, whatever the binary representation of 33 is. Double quotes is 34, hashtag is 35, 0 is 48, 1 is 49, capital A is 65, capital B is 66, small a is 97, small b is 98, so on and so forth. So what would the binary representation of small b be in ASCII? B की होगी whatever is the binary representation of 98, which is 98 की क्या होगी? Again we can use the formula. It will be something like end में 0 होगा, उससे पहले 1949 1 होगा, उससे पहले 24 0 होगा, उससे पहले 12 0 होगा, उससे पहले 6 0 होगा, उससे पहले 3 1 होगा, उससे पहले 1, something like this. I think this might be right. तो 1 2 3 4 5 6 7. This might actually be wrong also, I don't know. But just convert 98 to binary. That is the binary representation of an ASCII B character. आपको जिंदगी में कभी भी कुछ bytes मिली, right? Whenever you are talking to a machine via HTTP also, whenever you are transferring your data, a text message also on the other side, your friend को you send hi there, you're actually sending them a bunch of bytes only. You're sending them a bunch of zeros and 1. And then eventually Facebook का messenger interface understands कि यार I need to convert these zeros and ones back to ASCII, and that is why your friend sees hi there. What you send to your friend looks something like this. What you send to your friend when you say hi there, what leaves your machine and goes through a bunch of wires and gets read by the other machine's CPU and put in RAM is something like this. ASCII is the most popular, encoding in which websites are written, which is why it gets decoded to something like hi there. But if you don't use ASCII, if you use something like hex, then it might get, decoded to something like this. Of course, us humans understand alphabets, we understand the English language, which is why ASCII is the popular, medium in which these bytes are decoded back to. Hopefully, ASCII is clear. Here is some Node.js code to convert binary to ASCII. If you don't understand coding, JavaScript right now, I'm not going to go too deep into this. But if you do understand coding, I think most of you know JavaScript. I've written a function, bytes to ASCII. It takes a byte array as an input, and it just calls from char character on that byte, from char code on that byte, and dot join will just convert the array to a string. By the end, these bytes will get converted to something like hello, because this is the binary representation of hello in ASCII. In UTF-8, it might be something else. In hex, it might be something else. In ASCII, if you take these bytes and decode them to ASCII, it represents hello, which you and I can understand, you and I can read. It's unfortunately very hard for us to read this. We cannot tell ये hello लिखा है unless we go to the ASCII table and start to match. कि यार 72 किसका था? अच्छा 72 was uppercase H. ठीक है, तो the first one over here represents H. 101 किसका था? I go over here and try to see 101 is, okay, it's E. So I can do this one by one करके match. Or I can write a program for it that will take these bytes, convert them to hello and output hello on the screen. You can use convert bytes to ASCII. You can convert ASCII to bytes as well. If you have a string called hello, you can call this function which calls ASCII string dot char code at I. ये थोड़ा गलत क्यों लग रहा है मुझे? At I. Oh हाँ, नहीं, this is fine. ASCII string dot char code at I would return for this thing 72, for this thing 101, so on and so forth. And then finally you create an array out of it and return it. If you log it, you will see hello key binary representation in ASCII is this. This when converted to ASCII in human readable string format converts to hello. तो ये सबको समझ आ गया? ASCII encoding. There's also something extra called uint8 arrays in JavaScript. Let's not go there, but something sort of important to deal with eventually, and how bytes are actually stored in JavaScript, or bytes should be stored in JavaScript. But before we get there, do we understand ASCII? Let me relaunch the pool. Okay, most people understand. I'm going to speed this up then. ASCII is one way you can store bytes or showcase bytes to users, makes sense for human readable messages. But there are other encodings as well. For example, hex. In case of hex, if you are given a bunch of bytes, you take them in chunks of 4. So the first 4 bytes can either represent 0 or represent a number as big as 15. If you take 4 bytes, to the smallest number that 4 bytes can represent in binary is 0, 0, 0, 0. If you do the math, this is 0. The second biggest number they can represent is 0, 0, 0, 1, which is 1. And the biggest number they can represent is 1, 1, 1, 1, which is 15. So the binary, the hex representation says, here if the first 4 bytes are 0, then in hex they will also be 0. In case of ASCII, there was something else. In case of ASCII, 93 was not 93, it was backslash. 91 was not 91, it was ye. But in case of hex, if you take 4 bytes and they become decimal 0, they remain 0. If they become decimal 1, they remain 1. If it is a decimal 9 number, then it appears as 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 appear as such. If it's 12 in if it's 10 in decimal, then it appears as, I think some of you might already know this, A. If it is 11, then it appears as B. If it is 12, then it appears as C. If it is 13, then D. 14, then E. And 15, which is the maximum it can be, then F. So the character set for hex is 0 to 9 and A, B, C, D, E, F. That's it. अगर आप एक byte array को, if you're converting a bit array or byte array to hexadecimal or hex, then the final output can look something like this. It cannot have Z in it. It cannot have Y in it. It will not have P in it. It will only have either 0 to 9 or A to F. That is just the hexadecimal encoding. Harkirat, फायदा क्या है इसका? What is the point of this when it is not human readable? There are many encodings that exist based on, whatever, 4 bits को ले रहे हैं या 8 bits को ले रहे हैं या फिर 3 bytes को ले रहे हैं, which could translate to multiple characters. If you want to, whatever, compress तो नहीं हो रहा data in this case, but an encoding that only takes 4 bytes at a time. Hexadecimal is a popular one. And in case of hexadecimal, unfortunately, the final output will always be non-human readable. It will always look something like this. 0, it might have some numbers. It might have A, B, D, F, E. It will not have anything else. It will never have O. It will never have P, so on and so forth. That's hexadecimal. So we have covered ASCII. We have covered hexadecimal. There are more. There is UTF-8. There is base 64, there is base 58. एक बार जल्दी से इनको भी देख लेते हैं, but there are just various encodings. Some of these encodings we will see as we create private keys, public keys, so on and so forth. The next one is base 64. It's very close to hexadecimal. In case of hexadecimal, you take 4 bits at a time. In case of base 64, you take 6 bits at a time. So what is the सबसे छोटा number that will exist? 0. What is the biggest number that can exist if you have 6 bits? It is 64. So it of course has 64 characters. Hexadecimal, I'm sure there is a link somewhere here. I'm sorry, base 64. Let's try to encode, something. This is ASCII to, let's not confuse you guys. I just want to see a base 64 table. In case of base 64, 0th binary, or 6 zeros represent a A. 5 zeros and 1 represents a B. And then chalte jao to, whatever. This 41 represents a P. And then, whatever. Karte, you will see more numbers. 59 represents a 7. 60, it basically is, all big characters, all small characters. 0 say 1, plus and slash. What does it contain? It contains all uppercase characters, all lowercase characters, all numbers from 0 to 9, plus and slash. That is the maximum final output subset that you will see. If you are converting to base 64, it will take 6 bits at a time. It will take, just in case of hexadecimal, it took the first 4 and spit out 5. Took the next 4, spit out 9. In case of base 64, it will take the first 6 and spit out whatever. A, let's say. Take the next 6 and then spit B, so on and so forth. That is what hexadecimal is, and this is the character set that it supports. There is something else called base 58, which is, it still takes, I don't know how many bits it takes, probably still takes 6 bits. It is similar to base 64, but uses a different set of characters to avoid visually similar characters and to make encoding more user friendly. तो इसने क्या कहा कि यार मैं सिर्फ 0 से लेके 57 तक ही सपोर्ट करता हूँ. I don't support 111 I don't support 111 I don't support 63 62 61. Base 58 is the same as base 64 minus some characters that look visually similar. For example, L and I look very similar. Uppercase I, lowercase L look very similar. Uppercase O and 0 look very similar. तो उसने ये characters को निकाल दिया. It removed a few similarly looking characters, and whatever is left is whatever base 58 encoding sort of things. इसके बाद एक और आता है UTF-8, which is 1 to 4 bytes. So it's basically 8 to 32 bits, which means it can store a lot of data. So in case of this, there are characters like these, characters like these. If you're ever writing in Latin or if you're writing in Spanish, if you're using characters like these, then they are encoded not in ASCII but in UTF-8, because UTF-8 supports, very big character set compared to ASCII, which only supports, whatever, some more limited 127 numbers. This or characters. This supports a lot of characters. 32 bits is, 2 to the power 32, 10 raised to the power 9. मतलब बहुत सारे characters को ये support कर सकता है. This only supports 127 characters, so small a.
It is September 8th, 2023, and you're watching the Code Report. Yesterday was a huge day for soy devs. Mojo became generally available, a superset of Python that's up to 35,000 times faster. But JavaScript also got way faster thanks to a new Swiss Army knife called Bun, and that means it's time for some new stickers on my MacBook Pro. JavaScript developers have grown tired of reinventing new frameworks, so now we're building entirely new JavaScript runtimes. In the beginning, we had Node.js, then rearranged the letters to make Dino, and now we've got Bun fresh out of the oven, which just hit 1.0 this morning. And you should take notice because it can run your JavaScript code faster than any other tool known to man. But not just that, it also acts as a bundler like Webpack or Vite, a test runner like Jest or Karma, and a package manager like NPM or Yarn. In addition, it's almost fully compatible with existing Node.js APIs, but has its own set of highly optimized APIs that actually make it fun to build high-performance server-side applications with JavaScript. Before we get into it though, I want to show you another awesome new tool from our sponsor, DevGPT. By now you've heard of tools like ChatGPT and Copilot, but DevGPT takes AI code generation to the next level by integrating directly with your Git repo, giving the AI the full context of your tech stack and project. After writing a prompt to fix a bug or create a feature, it'll ask follow-up questions to write highly targeted and useful code. Once the code is generated, you can then sync those changes to your local project instantly. Then you could prompt it to generate some unit tests to validate that code. It's like having an automated engineer by your side who can take care of your GitHub issues and Jira tickets instantly without complaining. You can try it out for free yourself right now with the link below. But now let's get back to Bun. First of all, how do they make this thing so fast? One major difference compared to Node and Dino, which uses the V8 engine from Chrome, Bun uses JavaScript Core from Safari, which is known to be optimized for faster startup times. In addition, Bun is implemented in the Zig programming language. They've put a focus on profiling performance bottlenecks and implement APIs in native code. The end result is a hello world with TypeScript that's 5 times faster than ES build. Keep in mind though, benchmarks can always be cherry-picked and rarely reflect real-world performance. It's fun to go fast, but because I only have 12 monthly active users on my website, it doesn't make a huge difference for me. What I care about is the developer experience. Can Bun make my life easier? Well, first up, it's got awesome TypeScript support out of the box. You can immediately start writing TypeScript code without any configuration or headaches. And it also supports JSX and hot reloading, which means you don't need any weird dependencies like nodemon and concurrently to recompile your code when things change. That's cool, but one of the absolute worst things about Node has been the transition from common Node.js to ES modules. What's cool about Bun is that you can just use import and require in the same file, and everything just magically works. And it's compatible with existing Node.js packages, which means you don't have to reinvent the wheel for every little thing you want to implement. Dino also added NPM support as well recently, but what I really like about Bun is its native APIs. For example, to read and write to the file system, we can access the global Bun runtime and make a reference to a file, then lazily read it or parse its JSON. That may not seem like a big deal, but in Node.js, there are 3 different ways to do the same thing: read file with callbacks, read file with promises, or read file sync. You can actually use all of those in Bun, but not only are the native APIs faster, they're easier to use. In addition, it's extremely easy to set up an HTTP server in Bun by simply calling the serve method. You then use familiar browser primitives like fetch and response to build your API. That'll take you pretty far, but there's also frameworks that work with Bun like Elysia that claims to be 18 times faster than Express.js in Node. Bun also works with Hano, which has been my go-to framework for building APIs recently. Bun has tons of other simplifications as well, like it makes WebSockets nice and simple out of the box without any extra dependencies, and you can use environment variables without things like .env. Pretty cool, but as the name implies, Bun is also a bundler. The Bun build command will take all your source files and then combine them into a single output that can be used in a browser. And based on this benchmark, it's pretty amazing how much faster things have gotten just since Webpack 5 a couple years ago. Oh, and another really cool thing is that Bun has a SQLite database built directly into the runtime. It's incredibly convenient to have a relational database without the need to install and configure a bunch of drivers. Another thing we need to talk about, though, is the Bun package manager. That's up to 25 times faster than NPM, and it's actually a standalone tool that can be used in any Node.js project today. If you want to make things go faster right now, replace npx with a command like bunks cowsay hello world, which allows you to save a few precious milliseconds when saying hi to your mom, which is important because you never know how much time you have left to do that. This has been the Code Report. Thanks for watching, and I will see you in the next one.
4.5 minutes. It fucked my brain. We don't know anything of this. I don't know anything of this. Probably I'll spend the next week building this thing, or like learning these frameworks or whatever this thing is.
A, small a to z, capital A to z, numbers, a bunch of special characters.
Oh,
so on and so forth.
the reason why I went back from this video to Bun, to checking out Bun, is because since he's discussing mostly about encodings and different types of characters and encodings and decoding, so basically now I'm using this browser called DIA, and this browser is really fast, and probably this browser is also made from Bun, I assume. Let's check it out. DIA browsers. What do we ask? Browser tech stack. Is a proprietary AI native. Chromium based. Chromium open source project. Oh. Chromium. Maybe this. Okay. Written in Swift. Swift basically runs on C++ or #C. C++ is primary. Blink and V8 implements HTTP. CSS, JavaScript, TypeScript. Fuck brightness so much. Both Objective-C and Swift. Python is my language. Okay, it's written in Python and C++. Maybe can we do inspect? Okay, we can do inspect. It's a Chrome website. Console. Okay. Okay. Back to our bun. So it has been released over 2 years ago. It's being really used by most of the other industries. So I thought, let me also quickly learn and check how faster is it in comparison with JavaScript or Python. But let's say there is another video here 4 months ago.
Bun is an incredibly fast all-in-one JavaScript toolkit for building, running, and testing JavaScript and TypeScript applications. 2 years ago, we released Bun 1.0, and since then, Bun's monthly downloads have grown over 47 times to now over 5 million monthly downloads. Every part of Bun is designed to be and to feel fast, from the runtime to the package manager to the test runner and to the bundler. And today, we're introducing Bun 1.3. We're pushing the limits of hardware performance, and we're making building with JavaScript faster and simpler. We've taken all the feedback from teams running Bun at scale. And in Bun 1.3, we've made improvements that make Bun even more stable, more compatible, and more production ready than ever before. If you're migrating your production workloads to Bun, send us an email.
You notice the previous guy was reading on a screen something. So I wanted to create something where you read and then it follows according with your live translation, like step by step highlighting the next word. I wanted to build like that. Maybe I'll check it out.
Bun is pushing the boundaries of what's possible with modern hardware in JavaScript. In Bun 1.3, we integrated JavaScript Core's garbage collector directly with Bun's event loop. This yields a 100 times reduction in idle CPU usage and a 40% reduction in idle memory usage for common production workloads. Lower idle CPU and memory usage means reduced hosting costs.
But Bun isn't just about performance. Bun is designed to be a drop-in replacement for Node.js. And since Bun 1.2, we've doubled down on Node.js compatibility. We've added an additional 800 new tests from the Node.js test suite that run on every single commit of Bun. And along the way, we contributed dozens of upstream tests to Node.js to improve their test coverage and reliability. If it works in Node and it doesn't work in Bun, then please file a GitHub issue in Bun's repository. It's our job to make sure everything that works in Node also works in Bun.
And adoptability has to extend beyond the Bun time. Today in Bun 1.3, we're introducing 2 of the most requested improvements to Bun install. First is seamless migration. Bun now automatically migrates log files from npm, pnpm, and yarn to Bun's text-based log file. This lets you switch from other npm package managers to Bun install with 0 configuration and keep your resolved dependency versions intact. Second is isolated installs. A common problem in large monorepos is transitive dependencies leaking into packages that don't declare them. These phantom dependencies cause the classic issue where code works on your machine but breaks on others. In Bun 1.3, we're making isolated installs the default, eliminating phantom dependencies and making installs even faster than before. In production-grade monorepos, Bun's isolated installs are over 70 times faster compared to NPM. Bun install is designed to work with existing Node.js projects.
Don't waste food like me.
Switch from npm, pnpm, or yarn in one single command, bun install. In Bun 1.3, we've added 6 new commands to bun install. First is bun update interactive. This command displays all available package versions and helps you choose which dependencies to update. Bun Y tells you why a package is installed by tracing which dependency pulled it in. Bun audit checks dependencies for security vulnerabilities, even after they've been installed. Bun info fetches package metadata from Node.js registries, pre-printing the manifest and additional useful information. Bun PM PKG makes it easy to get and set properties in package.json. And lastly, Bun PM version gives you a simple way to update your package version for a new release.
You can now import YAML files in Bun. This is great for configuration files, GitHub Actions, Kubernetes, and more. YAML imports are powered by Bun's built-in YAML parser, and we've also added support for YAML in hot reloading and Bun build. Bun's built-in SQL API now supports all 3 major relational databases: MySQL, SQLite, and Postgres. Our single SQL API now has automatic SQL injection prevention and drivers for all major relational databases. Bun now has a built-in Redis client, which means that you can connect to the world's most popular key-value store with 0 dependencies. It's fast, it's native, and it's as simple as importing Redis from Bun. Just get, set, and go.
Bun 1.3 comes with a big upgrade to Bun stability and reliability. Since 1.2, we've resolved over 2,000 GitHub issues, and I've seen rapidly growing production adoption. Thousands of companies bet on Bun as their default, from small startups the Fortune 500 enterprises, and even the world's leading AI companies. But don't just take our word for it. Here's what companies building with Bun have to say.
When we started Quad Code, we looked at a bunch of options for runtime. Bun was the winner hands down. It starts in like 3 milliseconds, and Python was like 15 times slower. For a CLI tool, that's the difference between an awesome user experience and something that feels sluggish.
At Midjourney, we use Bun's fast WebSocket server to efficiently publish millions of image generation notifications daily. Our production build time also went down from minutes to milliseconds.
At Railway, we built our AI functions experience on Bun, and it's allowed
For it. Thousands of companies
Just get, set, and go.
since one adoption. The first take
Started Quad Code, we looked at a bunch of options.
appears.
The Node.js project today important because you
Like learning this.
close to Bun.
for runtime, Bun was the winner hands down. It starts in like 3 milliseconds, and Python was like 15 times slower. For a CLI tool, that's the difference between an awesome user experience and something that feels sluggish.
At Midjourney, we use Bun's fast WebSocket server to efficiently publish millions of image generation notifications daily. Our production build time also went down, from minutes to milliseconds.
At Railway, we built our AI functions experience on Bun, and it's allowed users or Claude to deploy code in less than 1 second. And once it's deployed, it is crazy cheap. When customers Claude to deploy code in less than 1 second. And once it's deployed, it is crazy cheap. When customers switch to Bun, they save 60% or more on car insurance, on compute costs. And that's all before the changes in 1.3.
One of the best parts of Bun is its support for the Node.js ecosystem and its built-in tools. In Bun 1.3, all of the helpful APIs like S3 support, MySqueal, and the Bun shell work.
The customers switch to deploy Rail
Experience
Efficiently publish millions of image generation notifications daily. Our production build time also went down, from minutes
that's the difference between an awesome user experience
to efficiently publish millions of image generation notifications daily. Our production build time also went down, from minutes to milliseconds.
At Railway, we built our AI functions experience on Bun, and it's allowed users or Claude to deploy code in less than 1 second. And And once it's deployed, it is crazy cheap. When customers switch to Bun, they save 60% or more on car insurance, on compute costs. And that's all before the changes in 1.3.
One of the best parts of Bun is its support for the Node.js ecosystem and its built-in tools. In Bun 1.3, all of the helpful APIs like S3 support, MySqueal, and the Bun shell work wherever you need them, including in frameworks like Next.js.
At Replit, Bun powers performance-critical infrastructure that concurrently connects hundreds of thousands of users and their agents to their containers. This enables any TypeScript developer to ship performant backend code.
Bun is fast and cute. Bun runs and builds RealOS, Baby Cursor, and all my new ideas with Cursor Agent. The cute dumpling paired with lightning fast DX just hits different.
We wouldn't have gotten here without our incredibly active community across Discord, across X, YouTube, and GitHub. Thanks to hundreds of people who contributed to Bun 1.3. And for Bun, this is still just the beginning. To explore everything new, head to bun.com/1.3. To install Bun, visit bun.com/download or run any of these commands. And for Bun, becoming the default runtime is still just the first chapter. Is still just the first chapter. Becoming the default runtime is still just the first chapter.
This is why everybody loves Bun. Check this out. Bun does such a good job at making the hard parts of writing JavaScript really simple. So I'm writing this function here, download items, and I need to download a couple thousand files to my computer, right? So in order to do that in Bun, you simply just make a Bun file, and you can check if it already exists or not. No checking if some weird API if the file exists. No checking to make sure that the folder is already created. You simply just make a Bun file, and that is a lazily loaded file. You can check if it exists, and if not, you simply write a file. And get this, you can pass it. Of course, you can pass it. It's simply just download themes.
Welcome back to the Ultimate Zig course. I know I already have a Zig course on the channel, but as you may know, ADHD mixed with OCPD doesn't exactly let you continue something you started a long time ago. Of course, I won't delete the old videos. I think they're still very useful for anyone learning programming for the first time. But let's be honest, I didn't really talk much about Zig itself, mainly because the course was never completed. Anyway, shall we try again? Wait, before we continue, we need to agree on a few rules. Firstly, this course is about Zig, not about learning programming. I'll assume you're already a programmer. Secondly, episodes won't go over 3 minutes, so I can stay consistent and not repeat the same mistake again. Third, I'll focus on the content itself, not on showing off my editing or animation skills.
Which language usually wins? Zig, I think right now.
Zig is known for being fast, but in 2026, we already have a lot of fast languages. Rust, Go, and even C and C++ have become much faster than they used to be. So, is Zig fast? Absolutely. In many cases, it's faster than C. But speed alone isn't enough. The real question is, do you actually trust what your code is doing? Let me show you an example. In languages like C++, D, and Rust, this code hides a lot of things. Firstly, the hidden control flow. In D language, the expression C.D might actually be in property function, which means a hidden function call. In C++, D, and Rust, the plus operator can be overloaded, so that's another hidden function call. In C++, D, and Go, the foo function might throw an exception, or panic in Go, which can completely prevent the bar function from running. Secondly, the hidden allocations. In Go, defer allocates memory on the function local stack, and it can fail with out of memory. In C++, coroutines allocate heap memory. In Rust, many standard library APIs panic if memory allocation fails. And the problem? All of this is hidden. There's no way to know just by reading the code. This isn't a feature. It's a problem for readability, maintainability, and reusability. But for Zig, it takes a different approach. If we try the same first example, we will find that Zig guarantees exactly what you see. It calls foo, then it calls bar. Nothing more, nothing less. And you don't even need to know the types. How? Well, no operator overloading. Plus means addition, not a hidden function. No property functions. Function calls always show parentheses. No hidden exceptions. Errors are returned, not thrown. You'll see try or catch when errors are possible. No hidden allocations. Allocations need explicit allocator parameter. So, the golden rule is, what you see is what you get. No surprises. Is Zig easy to learn? Well, honestly, no. The syntax isn't the most beginner-friendly. The naming conventions could be better, and mostly you'll write more code than you would in other languages. But here's the thing, that's intentional. Zig gives you complete control, total transparency, and no hidden behavior. And about that complexity, well, I think this is the price of working at this level. Well, we've got about 10 seconds left to hit 3 minutes. Use that time to leave a comment. It'll motivate me to make the next episode about the Zig compiler. See you next time.
I'm wondering, because I haven't actually spoken to how you like in the conference so far.
It's great. Yeah. Really fun talking to people and walking around.
Have you been to either React Summit or JS Nation before?
No, not numbers. I did get, I think, I don't know. Yeah, no, The initial version of Bun was basically me working for a year in my like just like really very code time, and then we got the idea where like you had like server like I want Bun, and like more than else with that. I think the first week of the book we like to get the start chart with a straight line. Very cool. Yeah, it was like about 10,000 start on that. But just really, let's go. Yeah, just over time we raised a lot of money and more and more Bun. What do you like building a start? Is it the speed performance? Is it the wins that you see? Is it because it's for developers? I've been really frustrated for like years how slow everything else is. Yeah, because the computers are really fast now. So why build our software really fast too? The answer to that for the job. So what do you think? For developers, I'd been really frustrated for like years how slow everything in JavaScript is. Yeah. And because like why like our computers are really fast now. So why doesn't our software feel fast too? The answer to that for the JavaScript ecosystem is a mixture of a lot of overlapping tools that duplicate work, and then that also accrues paper cuts. A lot of like small things that don't really work super well, or you have to add all these workarounds. Like why can't you use import and require in the same file? Why does JSX need a build step? There's a lot of things that are just more complicated than they need to be. And I've spent a bunch of time as a front-end engineer before working on Bun, before learning a bunch of systems engineering stuff. I think back on that time a lot and use that as like product prioritization, really to inform my thinking. Yeah, I mean, I think the products that people build where they themselves are user and they're building it for like fast version of themselves, that's incredibly powerful. Because it's such a good reference of what game really means like on a day-to-day basis. So I get that you get enjoyment out of kind of solving that. But it's completely different from building a game, for example. Like, yeah, has all the visual components, one doing the same thing. I think I shouldn't have actually worked on the game. That was really stupid. Okay, how's that? I actually like working on the game. I didn't like building the gameplay parts of the game. I like working on the tooling. Gotcha. So I spent more time on the tooling than the game, and then I was like, well, doing all the time on tooling. So it's a natural fit to do that. Yeah, it makes sense. So Bun, I think was stable production release 2023. Out of the completely. Yeah, we don't know released a little over a year. Yeah, I was also this. It's doing really well. I think the companies are using Bun was a for a lot of the code. Yeah, they're great. The ice block. So it's like fun, like they're using something that I'm. You can be proud of that for sure. That's awesome. Yeah. And then since kind of cloud code adopted it, there are other competitors out there, right? Because I also think easier to get time from Dino. Dino's been there as well now. People are taking different things. Why would they bet on Bun in the first place? What would you say for that? Generally, we make Bun. We have Bun because it's the Node.js ecosystem. Most of our engineering time is actually on features is spent on. Node.js compatibility. Node.js tests we pass in Bun. Today we run a little over 2,000 tests from the Node.js tests we run every single commit. A lot of the built-in modules in Node app. Thank you. It generates so take it up. You probably just want to set basically about there's like okay, only reaching more, so it's easier to achieve that goal. We're not yet at 90%, but we're getting there. Yeah, it's going to achieve what you think to make it an easy job replacement of animals. And large based. Yeah, the other one is large based. Most of the work on it. Is getting that number to about the percentage. So no additional features, no functionalities. We are still working on new features, but like the percentage of time is like 95%. On like okay, like this test we have. Honestly, it's actually we're saying immediately too much on it means that the number of issues goes up because the new tests that we're trying to don't always include issues. Yeah. Often actually overlap like this. There are real problems our users are running into. But it's really constant because we see the end of the year for getting us to like where the number of compatibility is going to issue. And so we really just want to get done. You aim to reach 100%. Because I also wonder if there's a trade-off of let's say the first arbitrary 89% is like X number. Last 10% might be slightly more. My guess is that like they're going to call some percentage where we're comfortable with it, but we're not there yet. Gotcha. And it'll probably be pretty obvious because we'll start getting issues done. Exactly. It'll just be smooth. Yeah. Okay. Interesting. But I love that you have this kind of goal set. That's very specific, very concrete, something you're trying to work towards. And you're motivated to do so. Yeah. We on the office on the TVs we have which is the current percentage. And we just make that number up. Yeah. It's simple as that. You mentioned you started this by yourself for a long time. I can hop on board and let's like now. Yeah, so we've raised a colleague that raised around today we're 40 people full-time all based in San Francisco. Oh, yeah. Are you the person that like orchestrates things of vision and does I'm the CEO and also I store a lot of code. Honestly, I probably spend time writing code. Really like time writing code, really like code. 40 people, you're 40 people. Yeah, that's good. That's really healthy. Do you think some of those shift, right? That's what you see in startups like scale-ups that grow to a size of 100, the whole CEO will change. Yeah. And I think it's gonna be hard to going part. Yeah. Will that be you think? Address that forward, or will you stick to more of the coding principles? I really write code, but also want to do a startup. Yeah, SEO, and so probably I'll end up more with SEO. But today I'm very much an engineer. Yeah, I like that. I mean, it's gonna be trade-off. Like, what do you do? What do you enjoy? What does the company need? And if that's you want, you can do it because it is you. And then see how it goes. But that's gonna be quite far. Right? Do you think how long will it be for you to get to the stage where you actually start scaling with regards to engineering capabilities and grow faster? I don't know. The first step for us is we get no compatibility to be solved. Do that, then we'll see. Yeah, there's no roadmap for after that. Like the features that you want to we're still going to build a lot of stuff. Very random things that I've been using for a while. I want to do email, time building, and the first email. Because like there's a lot of things built. parameters really nice, really productive. And I think that is an ecosystem, not the framework level, but the lower level integration level of like, okay, I'm never going to build a real production app. There's a lot of stuff that I think about. A lot of microservices that are actually important to shaping the code, but you have to make them just to do anything. You have to like, that's how I think.
Can we just take a minute and get Juicy together? Yeah, that's weird, right? Someone said that, you might be freaked out. But I'm talking about Zig. I'm talking about Juicy main, which actually was versioned not too long ago. Yeah, I feel like we should talk about it. So really quick shout out too. So if you are holding out like me on those actual releases, those qualified releases, you're not going to be able to do that. You have to wait until 16 or do a build from dev like myself. By the way, really quick, if you're using these, to do that, you can just install Zig at master and then also use global Zig at master, and then you're good to go. Okay, so I'm going to make a new folder here. We're going to call it Juicy, and we're going to cd into Juicy. Yeah, it's empty. So let's zig in it, and we now have a build.zig and build.zig.zon forward zig minimum zig version 0.16.0. So we got a couple things going on. So let's take a look. So if I open up main.zig, you can see that we have this new init method here in our main function. So our main function has changed. I probably shouldn't have called this Juicy because it is actually a little confusing seeing the word Juicy up here. This is the library. So if we look at our files in the file system in source, you can see that there's root.zig and main.zig. Root.zig is being exported as Juicy. We don't need it for this, so I'm just gonna go ahead and delete it. Okay, so we have a couple things going on. Let me just go ahead and remove this as well. And we don't really need our tests. We don't really need our fuzzing. So yeah, so what are we looking at? 17, maybe 18? Yeah, okay, cool. Yeah, so let's talk about this new Juicy main. I minimized this, so it's just the stuff that we need to focus on. We have our standard library like you'd expect. We have the big I-O, like big I, capital I, lowercase o, for the new I-O package that has been introduced as of 0.15 and will become the juice of the Juicy main. So this, you can call this whatever you want, and it's probably going to be the pattern that people tend to use because it's going on, and we can find it here.
ये सारी इनकोडिंग्स होती हैं. This is how data is stored / encoded / decoded from bytes. The one that you and I want to store strings in is either UTF-8 or ASCII. We use either ASCII or UTF-8 to store, our human readable strings in the RAM, in memory, so on and so forth. Do we understand encodings and various types of encodings we have covered? Solana specifically uses base 58. for encoding slash in the characters. UTF-8 because UTF-8 supports very big character, which is there are characters like these. If you're ever writing in Latin or if you're writing in Spanish, if you're using characters like these, then they are encoded not in ASCII but in UTF-8 because UTF-8 supports very big character set compared to ASCII, which only supports some more limited 127 numbers. This or characters. This supports a lot of characters. 32 bits is 2 to the power 32. 10 is for 9. बहुत सारे so on and so forth. B is our human readable strings in the RAM, in memory. So T8 for encoding slash showing public keys. If I open my phantom or whatever Soulflare over here and copy my public key from here, let's say whatever I copied, and if I whatever paste it some portion of it over here, this is a base 58 public key. The public key that I copied from my Soulflare wallet, the public key that I have on Solana where I'm holding some funds is actually a bunch of bytes, but the way it is represented slash shared amongst you and I, if I'm sending a friend some funds, I will ask for their base 58 public key. That's just the standard in Solana, which is why we're learning about these encodings. All right, 3 more topics before we get into the interesting things. Let's finish them off really quickly. They're very simple. Hashing and encryption. Hashing, thoda cryptography specific concepts. Hopefully we understand bits and bytes and encodings until this point. We started off with why cryptocurrency was introduced, फायदा है नहीं है, should it be used, should it not be used, some discussions around gold, some more computer science specific concepts like bits and bytes and encodings. Next we're understanding hashing and encryption, which is again cryptography specific concepts. Hashing is the process of converting data like a file, a message, some numbers, some text into a fixed size string of characters which typically appears random. If I hash a message hello using some hashing algorithm, the final thing that gets spit out is a bunch of random looking characters of fixed size. Could be 127 bits, could be 256 bits, could be 8 bytes, could be 32 bytes, but a fixed size output given an input like hello. इसका फायदा क्या होता है Harkirat? Where is it used? It's used various places. It's used in if you've ever tried password hashing, it's a common thing you might have heard in full stack. If you've done full stack development, if you've ever stored users' passwords in databases, you typically hash them before storing them in a database. If you ever go to a website and click on reset password, and if they are emailing you your password, that means that website is not following standard security practices. Generally, when you put a username password on a website, click on submit and sign up, their database doesn't store your password in plain text, it stores a hash of the password. Why? How does it eventually sign you in? Are different full stack questions we'll get to in the full stack cohort. But that is one place where you use hashing algorithms. Here are some common hashing algorithms. MD5 a little more weaker, SHA-256 a little more, resistant to attacks. Why? There are some differences over here, you can look at them, but mostly use SHA-56 today for hashing. Hashing follows some properties that should have been written over here but aren't. But hashing is irreversible, by which I mean, given a hash, you can't ever get back the original key without brute forcing. The only thing you can do is you can start to brute force every string over here. You will brute force A, B, C, D, E, F, G, H. You will find its outputs. You will compare it with this. You will keep brute forcing until you reach HELLP and then HELLO. And then you hash HELLO and then you compare the final outputs. There is no way to go from here to here without brute forcing the input. That is one of the properties that hashing has. The other property is if you go from HELLO to HELLP, the final output looks drastically different. In fact, we can go to a SHA-256 hash online, and you can try to see hello when converted via SHA-256. This is the output. HELLP the output is significantly different. HALL, L, the output is significantly different. The output changes drastically even if the input changes a little bit. The probability of collision is extremely low. What is a collision? Finding two words like hello and then Harkirat. Finding two words जिनका output same होगा, the probability is lower. It's not zero. It cannot be zero. This is fixed size, right? ये maximum 32 bits है या whatever, 128 bits है या 256 bits है. If the final output is 256 bits, if you try more than 2 raised to the power 256 strings, of course 2 of them will match. Output limited है. If I keep trying infinite number of strings, of course I will find two which have the same hash, but it's computationally infeasible to find two. दो ऐसे ढूंढना बहुत मुश्किल, next to impossible है जिनका hash same होगा. That's another property of hashing algorithms. Encryption is something slightly different from hashing. Encryption is the process of converting plain text data into unreadable format. Hashing is very similar. Plain text data into unreadable format. Called ciphertext using a specific algorithm and a key. So what is one difference between hashing and encryption? This तो नाम ही बता रहे हैं. Encryption can be decrypted. Hashing is one way, cannot be decrypted. That's the difference. Okay, when you do encryption, you can encrypt it using a secret, a private key, and as long as you have that private key, that secret, you can also decrypt it. The data can then be decrypted to its original format using the appropriate key. It is reversible. Hashing was not reversible. The security of encryption relies on the secrecy of the key. अब आपकी key अगर 1 to 3 random है, then of course someone will be able to decrypt it. But if your key is very solid, then people will not be able to find the input given the output. And it is of two types. Encryption is of two types: symmetric encryption and asymmetric encryption. We'll deal more with asymmetric encryption, but let's understand the two types. What is symmetric encryption? If you given some text, if you use a key to encrypt it and use the same key to decrypt it, it's called symmetric encryption. It means the encoding and the decoding process, the encryption and the decryption process used the same key. What is asymmetric encryption? If during encryption you use a different key, sometimes the private key, sometimes the public key, and during decryption you use the other key. During encryption you use the private key. During decryption, you use the public key. So you will have two keys to maintain in case you are using asymmetric encryption. If you're using symmetric encryption, then एक ही key से encryption, एक ही key से decryption. Again, many algorithms exist for this. There is some code over here. Let's look at what this code is. There's a lot of code over here. But there are two functions, encrypt and decrypt. If you call hello world with the encrypt function, it will return you some ciphertext. If you call the decrypt function, this one, one right of A. So you will have two keys to maintain in case you are using asymmetric encryption. If you're using symmetric encryption, then एक ही key से encryption, एक ही key से decryption. Again, many algorithms exist for this. There is some code decryption process used the same key. What is asymmetric encryption? If during encryption you use a different key, sometimes the private key, sometimes the public key, and during decryption you use the other key. During encryption you use the private key, during decryption you use the public key. So you will have two keys to maintain in case you are using asymmetric encryption. If you're using symmetric encryption, then एक ही key is encryption, एक ही key is decryption. Again, many algorithms exist for this. There is some code over here. Let's look at what this code is. A lot of code over here. But there are two functions in encrypt and decrypt. If you call hello world with the encrypt function, it will return you some ciphertext. If you call the decrypt function, this one right here, with the ciphertext, you will get back the original decrypted text. You can print all of them and see कि हाँ सब सही है. So encryption, decryption is different from hashing. Hashing is a one-way function. Encryption, decryption are two ways. We will dive deeper into / deal more with asymmetric encryption. This is how, crypto is sort of owned by people. आप और मैं crypto कैसे own करते हैं? Using public private keys. You might have heard of them, might not have heard of them. We'll see them very soon. But if you do want to hold crypto today, अगर आपको आज कुछ crypto currency hold करनी है, then you might buy it on WazirX or CoinDCX. That's a separate thing. But if you truly want to hold some cryptocurrency, अगर आपको actual में cryptocurrency hold करनी है, and you don't want it delegated to WazirX, you don't want it delegated to CoinDCX, तब you have to yourself hold public and private keys. आपको खुद को एक public key बनानी होगी जो आप दुनिया के साथ शेयर कर सकते हो, that you can share with the world, where people can send you funds, and you will have to create a private key that only you should keep with yourself, that you will use to not exactly encrypt messages but sign messages, so that people know कि हाँ ये आपने message भेजा है. One thing is encryption, जो अभी हमने देखी कि you can use something to encrypt a message and decrypt it. The other thing is signing messages or digital signatures. क्या क्या पढ़ा हमने? We learned about bits and bytes. We learned about encodings. बहुत सारी देखी, hex देखी, ASCII देखी. Next we saw hashing. ज़्यादा काम की नहीं है हमारे. We saw encryption, which is of two types: symmetric.
There is a small insect on my screen and it is really bugging me. Fucking small bug. Yeah.
Asymmetric. And we saw encryption is used to encrypt using a private key, decrypt using a public key. That is one thing. The second thing is encryption can be used to sign messages. What does signing messages mean? Basically, it's very close to signing a check. If I have a check today and I sign on it, a bank can verify ये हरकिरत के ही signature है. Similarly, if I have a public-private key pair, if I have a public key that looks something like this and a private key that looks something like this, let me just call it, pub key and private key. I can actually sign messages like this. Send one sol to a different public key. Let's say my दोस्त की public key, pub key 2. I can sign this message using a private key. Basically means running some function, some not exactly encryption algorithm, even though the final output will be very random and the final signature will look something like this. It will not be plain text like this. But technically, I am not encrypting, I am digitally signing using my private key. And anyone all around the world can verify कि हाँ भाई, verify using my public key. Anyone around the world can verify using my public key कि हाँ ये मैसेज तो हरकीरत की प्राइवेट की से ही साइन हुआ है. That means this message was actually signed by Harkirat. I will repeat myself. If I open my wallet over here, Soulflare wallet, it has some $9,000 in it. If I copy its public key and show it to everyone, you guys can have access to my public key. Let's say it looks something like this: 8K, 8XZ, some base 58 encoded string. It's private key only I have. If I open Soulflare, click on send, put like one soul and put my friends, whatever, public key over here and click on send. When I click on send, what happens is a message like this gets signed by my private key. मेरी private key इस wallet में exist करती है. Somewhere here inside there is this private key. So when I click on send, this message is signed using my private key, जो मैं आपको नहीं दिखा रहा हूँ. Public key I have shown, private key I have not shown. When I click on send, this digitally signed message and my public key get forwarded to some Solana miner who verifies using my public key कि हाँ indeed हरकीरत ने ही send दबाया है, हरकीरत ने ही ये message भेजा है, and hence we can actually deduct हरकीरत's one sol and increase the one sol amount on this other public key. So where does digital signing / asymmetric cryptography / public and private keys come into the picture? Okay, today if you want to receive some cryptocurrency, some Solana, some BTC from someone, you will first create a public private key pair. You will, using some famous algorithm, create a public private key pair. Solana has one algorithm it follows, EDDSA, ECDSA. We'll come to what the name of the algorithm is and how it creates public and private keys. But Solana has a specific algorithm, Ethereum has a specific algorithm, BTC has a specific algorithm that you can use to create a public and a private key. उसके बाद वो public key अपने दोस्त को दे दो, he can send you Solana. And if you want to send someone Solana, then you will sign the message using your private key, give it to the blockchain. The blockchain knows कि अच्छा इसी बंदे ने भेजी है, तो इसका balance मैं कम कर देता हूँ. And let me increase the balance of the other guy because it is digitally signed. That is the purpose / usage of asymmetric encryption in blockchains. In blockchains, you सबसे पहले create a public and a private key. It will be empty. It will not have any BTC in it. You will randomly generate a public private key. Anyone around the world can randomly generate public private keys. There is almost never a collision because there's like not infinitely many, but 2 raised to the power 256 possible outcomes. So very low probability if you randomly generate a public private key pair and I generate a public private key pair. I call it a key pair because it creates a public key and a private key. Very low probability we get the same one. So if I generate one randomly, I will most probably have won't have any Solana in it, won't have any BTC in it. I can give that public key to a friend. He can send me some BTC. Now the full blockchain feels like I have one BTC. And if I want to send it to someone, I will sign that message. Okay, I want to send this much BTC to this other address using my private key. I will take this signature, forward it to the blockchain. The blockchain will not exactly decrypt, but verify my signature and confirm कि हाँ हरकीरत की private key ने इसको sign किया है. That means Harkirat has approved this message. He wants to send one sol to the other guy. What are these common encryption algorithms / how public private key pairs are generated? RSA is one. It is not used in cryptocurrencies or Bitcoin, Ethereum, Solana, but is popularly used other places like digital signing for certificates. If you look at these SSL certificates or general cryptography, if you're doing any of these CTF challenges, you will see RSA as one encryption decryption algorithm come. For BTC and ETH, they use one called ECDSA. For Solana, it uses one called EDDSA. ECDSA, EDDSA. elliptic curve digital signature algorithm is the algorithm you will use, which basically translates to अगर आपको public private key बनानी है तो you will import ECDSA from @ECDSA/library and then you'll call ECDSA.generate to generate a public private key pair, which under the hood of course has the logic that whatever this paper describes as the way to generate public and private key. For Solana, they use something else a little more optimal, EDDSA. The way these generate public and private keys is using something called elliptic curves. Here is a video by Computer File that dives a little bit deeper into this in case you want to understand how elliptic curves work and how a public private key.
So when we looked in the last video, my security overview for a particular website, we noticed it actually wasn't using Diffie-Hellman, it was using elliptic curve Diffie-Hellman. So this is just going to be a short video that explains broadly the difference between the two without going into too much maths. Although actually the maths of elliptic curves isn't that difficult. Let's not go over Diffie-Hellman a third time. So you and me have some kind of secret key and we use that to talk securely. Diffie-Hellman is how we get that secret key. Every time I talk about Diffie-Hellman and use any kind of analogy, people were like, oh, show us the math. So this is for the maths people. We had a few interesting questions on the Diffie-Hellman video, so let's explore. Remember that Alice here has some public variable g to the power of a mod n. Now, what's important about this is that in some sense, A has been mixed into this generator so that we can't split it up. She can send this around without everyone working out what A is, which is the important thing. So really, what the mathematics behind Diffie-Hellman does is allow the protocol to send messages where you can't, and Diffie-Hellman does, is allow the protocol to send messages where you can't extract this private variable. And that's exactly what elliptic curves do. They just do it in a slightly different way. What's important about some public variable g to the power of a mod n. Now, what's important about this is that in some sense, A has been mixed into this generator so that we can't split it up. She can send this around without everyone working out what A is, which is the people. We had a few interesting questions on the Diffie-Hellman video, so let's explore. Remember that Alice here has some public variable g to the power of a mod n. Now, what's important about this is that in some sense, A has been mixed into this generator so that we can't split it up. She can send this around without everyone working out what A is, which is the important thing. So really, what the mathematics behind Diffie-Hellman does, working out what A is, which is the important.
one thing. So really, what the mathematics behind Diffie-Hellman does is allow the protocol to send messages where you can't extract this private variable. And that's exactly what elliptic curves do. They just do it in a slightly different way. I'll draw a picture of an elliptic curve-ish, right? So this is an elliptic curve. Elliptic curves are curves in 2 dimensions.
We need colours on this, Mark.
Colours. It's the future. Right, so the formula for an elliptic curve is y squared is x cubed plus ax plus b, and that's the last time we're going to talk about it. So the parameters of the curve are a and b, and then the curve will look something like, hold on, I'm going to sort of take a bit of artistic license with this, but something a bit like that. Now, they vary in shape depending on what a and b are. The thing about an elliptic curve is, in our modular arithmetic, we had numbers going around modulo n, right, which is just a list of numbers, a cycle of numbers. Here we have a cycle of points somewhere on this curve. So our generator will be a point on this curve. Let's use blue, shall we? This is our generator. That's not a good place for my generator. It's not a good place for my generator because then my next example of adding things to the generator won't work. Let's do it there. Right, ignore that point. That can be a different point for later. Now, if this is our generator G, what we can do, instead of raising things to powers, we just add G to itself. We have 2G, 3G. 3G is G plus G plus G. Yeah? So what we can do is we can add G to itself. To do that, what you do is you draw a line at the tangent of this curve all the way until it hits another point on the curve. You flip it over to the other dimension, and this is 2G over here. 3G would be the line between these two, find out where it intersects, and flip it over here. So this is 3G. 3G plus G would be, it goes along here like this, intersects the curve somewhere else, flips over, and it's over here. So this is 4G. Now, we won't look at it anymore, right? The actual formula for this is just mathematics to do with line. Flip it over to G. Instead of, ignore that point, that can be a different point for later. G to itself, we have 2G, 3G. 3G is G plus G plus G. Yeah? So what we can do is we can add G to itself. To do that, what you do is you draw a line at the tangent of this curve all the way until it hits another point on the curve. You flip it over to the other dimension, and this is 2G over here. 3G would be the line between these two, find out where it intersects, and flip it over here. So this is 3G. 3G plus find out where it intersects, and flip it over here. So this is 3G. 3G plus G would be, it goes along here like this, intersects the curve somewhere else, flips over, and it's over here. So this is 4G. Now, we won't look at it anymore, right? The actual formula for this is just mathematics to do with lines and the tangent of this curve. It's actually not very complicated. The point is that what we're doing is by multiplying G by various numbers or adding it to itself, this point addition, we're moving around this curve sort of seemingly at random, right? A bit like how we were moving around our clock face seemingly at random. So the nice thing is that if you're adding points together, we talked a bit about end-to-end encryption already, and a lot of it The assumption is that we have some kind of symmetric key that we can use to talk privately. So you and me have some kind of secret key, and we use that to talk securely. Diffie-Hellman is how we get that secret key. Diffie-Hellman was first published in 1976 and has become pretty much a staple for any kind of cryptography at all. Right. Whenever we use cryptography, we usually need to have a symmetric key, and to get that, we often have to perform some kind of Diffie-Hellman. It's so prevalent that your phone is probably doing it right now. Right? When you logged onto the browser to watch this video, you performed a Diffie-Hellman key exchange. When you open up your phone and it connects to any server, it'll almost certainly perform a Diffie-Hellman key exchange. If not now, then in the next few minutes. Right? It's unbelievably important and unbelievably common. The problem with Diffie-Hellman is it's quite mathematically complex. It depends on your level of mathematics. So what I thought we'd do is I thought we'd cover the mathematics in the extra bits, and then we'd look at a kind of worked example of what actually happens as an overview for those people who are just not interested in the mathematics because they don't need to implement it and they don't really mind. So we'll do both, and that way, hopefully, there's something for everyone. We shall see. So perhaps Diffie-Hellman key exchange is slightly misnamed in the sense that what we don't actually do is exchange a key, because then it would be out in the public and we'd see it. What we actually do is exchange some public variables and we combine them with some private variables we've kept hidden so that we can both create the same key. Right? So we're actually creating a key together in some sense. So as always, we'll go back to Alice and Bob for this. So let's have Alice over here. Right, and Bob over here. I'm going to sort of spread this out a bit because we're going to bring these in and I don't want to run out of space. Right, so Alice and Bob are here. These are their own machines. And this is the kind of public area. So anything that Alice and Bob send to each other or agree on in public is going to be in this area. So as an attacker, if we want to break this key exchange, if we want to find out what the secret key is, we have to use these variables to do it. Right, and that hopefully will explain why that's difficult to do. Okay, so the first thing is, right at the beginning of the Diffie-Hellman key exchange, Alice and Bob have to agree some mathematical parameters that they're going to use. This is a value G, or a generator, and a big prime number N. Right, now, for this example, I'm going to use colour mixing to try and explain this. I'm going to write the letters in as well. N won't have a colour for the sake of this analogy. G does, right? So G is going to be, let's go with yellow, right? Now, I'm going to sort of squirt this in and hope that it doesn't go everywhere. In fact, we kind of need 2 copies of G, really. So let's just sort of fill it up here, up to about... I want to get them the same. So far, so good. So far, it's not all over my desk. All right, close enough. Right. Well, it's kind of yellowy. Yeah. Often, they're shared at the very beginning of the handshake. Sometimes they're just embedded in a standard, or everyone always uses the same one. It depends on the situation. It can take a little time, an extra message to send these things across. So sometimes having them stashed ahead of time is a good idea. So we've got G, right? This is G. Now Alice, to begin with, needs to calculate a private key, right, or a private variable. I'm going to choose red for Alice. There we go. Probably could have used more food colouring. It's kind of pale red. Is that red? Yeah, close enough. What do you think? It's rose-coloured. Now, Bob is going to do the same thing. He's going to have a private value, which is going to be blue. Right. Now, I haven't chosen very interesting colours. That's simply because there aren't that many colours available in the shops for food colouring. And I didn't go to that much effort. There we go. That's Bob's blue. Now, these 2 colours are in their private area. This is A and this is B, so I'm going to label these. This is little a, this is little b. Now, the important thing is that these are never shared with anyone. Alice doesn't share this with the public. Alice doesn't share this with Bob. Now, the first thing that happens is that we need to combine the private key with the generator to produce a public key. Right? Now, the point is that once we've combined them, we can't unmix it. Right? That's why people like to use this colour analogy. Once we've poured 2 colours together, it's difficult to know what colours went in. Right, because yes, okay, so if I pour red into yellow, it maybe make orange, but it could be that it was a bit more yellow and a bit less red, or, you know, it's difficult to know. Right, so it's kind of orange for Alice, and Bob's going to take his blue. I can't need them to be the same level, really. And it does kind of make green. This is a bit orangey. Let's not critique me too much. So, yeah, they're very different to the originals, and the important thing is that we don't know what went into here, right? We know G, but we don't know A, and we can't find out. So this is actually, this public key here, is a G in some sense. It's got an A in it, it's got a G in it, right? This one has got a B in it, and it's got a G in it. And we can't extract the A's. We can't reverse this process. Now, they then are going to exchange these two public variables, but keep the private ones back. So we're going to sort of draw an arrow over here and an arrow over here, and they're going to switch them like this. Right, so they get sent out in clear text. These are now in the public area because they've been sent in plain text, everyone's seen them. Right, so now, as an attacker, I know BG, or Bob's public part of his key, AG, Alice's public component, and G and N. Right, I don't know anything else. I don't know what A and B are. Now, this is the final part, Diffie-Hellman. Right? It's not actually very long. You can do all this in 3 messages. Alice is going to take the public component that Bob sent her and add her private key. And Bob is going to take Alice's public component and add his private key. So we're going to get, in essence, a mixture of A and B and G. Right, that's the idea. So let's do that now.
So is that in the private domain?
Yes, this will be done privately because these are never sent. So these go into the private domain now. I mean, I could make a copy of them. Let's not. So Alice is going to add her red in. So let's just add some red up to about there. Doesn't really work because the red's too faint. And then Bob adds in his blue, which is going to be like that. And hopefully, this is where it all doesn't work or does work. These two values are kind of the same. I mean, they're pretty close. That's a little bit darker, perhaps because the blue's a bit stronger.
Considering you've done that without actually measuring anything.
Yeah, I mean, obviously,
pretty good.
You would do this normally with mathematical functions that are much more precise than my random squirting of liquids. Now,
so those two are now in the private.
This is private. So Alice has taken Bob's BG and added her A, so that gets A, B, G, and Bob takes Alice's AG and gets A, B, G by putting his B in there. Right now, the order doesn't matter. Remember, just like mixing colours. The mathematics is such that if we add in B first to G and then we add in A, it's the same as adding in A first. So these two values are exactly the same. If you wanted to try and recreate this as an attacker, you can't do it because you have AG and BG and G. And so you could mix these two together and you would get A, B, G, G in some sense. Mathematically, this is a little bit tenuous, but we'll talk about that in the extra bits. The point is nothing in this public area can be combined in any way to get this value or this value, which are the same. The only way to do that is to find out what A and B are, and the only way to do that is to split up one of these two public components, which is very, very difficult to do. Right? And that's what's so cool about Diffie-Hellman. In a few messages, we've sent some public numbers around, and we've used our private numbers to get a shared secret that no one else can know. Now, you would generally do this at the beginning of every conversation, and you would use this number combined with perhaps some session variables, something like this, to derive secret keys for use in things like AES. Right? So this is actually just going to be a number which we would then hash to turn into an AES key or something like that. Now, the mathematics behind Diffie-Hellman is usually modular arithmetic. Recall that we have our public numbers G and N. G is often very small. It's usually a small prime number. N is often very big and needs to be big for the security of this to work. Every time I talk about Diffie-Hellman and use any kind of analogy, people were like, oh, show us the maths, show us the maths. I could have taken the maths. So this is for the maths people, right? If you want to know how mathematically Diffie-Hellman works, watch this video. If you don't want to know that, there's a nice close button in the top corner or a back button, be my guest. So this is for mathematically inclined people. Let's go back to where we were before. So we have Alice, and we've got Bob, and we've got our public area here, sort of public, and we're going to draw down here. Now, the mathematics behind Diffie-Hellman is usually modular arithmetic. Recall that we have our public numbers G and N. G is often very small. It's usually a small prime number. N is often very big and needs to be big for the security of this to work. N is often 2,000 bits long, or 4,000 bits is more common now. So N is very, very big. It can't be too big because you won't gain much in security, but you lose in efficiency. So, you have to think about that. Alice and Bob need to pick their numbers A and B. So Alice picks a number A, Bob picks a number B. These are the ones they're going to keep private. Now, A is somewhere between 1 and N, but it's random. And N is so vast that it's not going to be 1. It's going to be a very big number. Let's not worry about what it is. She's not going to tell anyone what that is. Same for Bob. The first thing Alice does is she calculates g to the power of a mod n. Right, now, modulo, if you do any programming, you'll be familiar with the percent symbol, is the remainder after division. So another way of looking at modulo is to have this kind of clock face. So if we have a clock face, which should be a circle, and we go from 1, 2, 3, all the way round to n. These are the numbers modulo n. So when we perform some arithmetic in this space, we just go round and round the clock face. We don't ever leave and go above n or below 0. In fact, this should be 0 as well. There should be a 0 in here. So when you do g to the power of a mod n, what happens is you're raising g to the power of some massive number, which would be very normally very big, but in actual fact, it just goes round and round this clock face and ends up somewhere. So let's say g to the a mod n arrives somewhere here on the clock face. Now, what's important about this is it's very difficult, given this, to work out what a was. Right? We know g is, let's say, 3. Right? If I say we're here on the clock face and we started at 3, what number is a? It's just impossible to know, right? Because its position on this clock has no bearing on how many times it's gone round or what a was at all, right? The only way to do this is essentially to brute force it, to go, well, is it a to the power of 1? No, it's not. Is it a to the power of 2? No. And then so on and so forth for an infeasible amount of time.
We did a little bit of this with the hashing video, didn't we? There was a little bit of the modulo function there in calculating the hash.
Yeah, so that was used to shorten something at the end, but it's the same kind of principle. Modulo is very useful for taking something that could be any length and putting it into a sort of finite loop, a finite group of actual numbers. Now, Bob, we're going to take g to the b mod n. So let's say that turns up over here somewhere. So this is g to the b mod n. So again, what we've done is we've taken g, we've raised it to the power of b, and we've done all of this modulo n, which means that it just, if it ever goes above n, it just loops back down to 0 and keeps going. So this is somewhere else. These are their two public components, so they share these like this. So now these are public, but again, calculating a and b from this is very, very difficult. It's called solving the discrete log problem, and practically very, very difficult for even a supercomputer. All right. Now, Alice is going to take this, I'm just going to simplify the notation slightly to make it fit on the page, but Alice is going to take the g to the b that Bob sent and raise it again to the power of a mod n. And Bob is going to take g to the a that Alice sent and raise it to the power of b mod n. And anyone that's done any exponentiation knows that if you do something to the power of something to the power of something else, it's actually just those two things multiplied. So it's g to the ab mod n. That's the answer. So that will come somewhere around, let's say here. All right, so this is g to the ab mod n. Now, this will be some number between 0 and n. Bob's done the same thing. He's also got g to the ab mod n, and they're exactly the same. These are the two identical colours we were looking at in our colour example. And mod n. Round, mod n. That's the answer. So, something to the power of something to the power of something else, it's actually just those two things multiplied. So it's g to the ab mod n. That's the answer. So that will come somewhere around, let's say here. All right, so this is g to the ab mod n. Now, this will be some number between 0 and n. Bob's done the same thing. He's also got g to the ab mod n, and they're exactly the same. These are the two identical colours we were looking at in our colour example. So they've both arrived at the exact same position in this group, despite the fact that neither of them knew what each other's private key was. That's what's really cool about Diffie-Hellman. To try and reverse this process, we have to know A or B. We know publicly g to the A, and we also know g to the B. If we try and multiply them together, for example, we'll get g to the A plus B, which is not the same. Right? That's me sort of mixing my public colours together in the hope of getting the right answer. I haven't got it. That would be somewhere else, a completely different number. Remember, this is cryptography. If you're one position out, it's not going to decrypt. Right? So, you have to get it exactly right.
The fact that she's got G to the B to the A is no different to G to the A to the B.
It's exactly the same. I mean, you could look at an example. If you went 2 to the power of 2 to the power of 3, that's 2 times 2 times 2 times 2 times 2 times 2, right? Which is 2 to the 6, because there's 6 of them. You can do it in any order. It doesn't matter. You get the same number out at the end.
Whereas that is a completely different thing.
Yeah, so that is equivalent of 2 to the power of 2 times 2 to the power of 3, which is 2 times 2 times 2 times 2 times 2, which is 2 to the 5, an entirely different number. Now, those numbers are fairly similar because these examples are small. You're just going to be somewhere else completely on this modular arithmetic clock face. It's not going to work at all.
The n number is kind of important, though, is it right?
It's mostly important that n is big, because if n is small, then in essence, this clock face is going to have only a few numbers on it. You can brute force that very quickly. Right, you can find the value of A or the value of B and reverse this process. If n is, astronomically large, like 2,000 or 4,000 bits, the amount of time it's going to take you to find the correct values for A or B is, essentially, is long enough that you won't bother. That's the argument. It's technically possible, but they'd be long dead by the time you did it, and so you finding out what image they sent each other is not that useful. Actually, this is quite simple, right? Let's not underplay it. This is incredibly important for computer science and mathematics, but it's actually not that complicated in some sense. It's very elegant. If you want to see some worked examples of this, Wikipedia and other websites have lots of small examples with small numbers, so that you can work this through if you want to have a go at the maths yourself, right? And you'll get the same answer out, and it's impressive. We had a few. We had a few interesting questions.
Hello, 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 hello. Hello, 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 hello. Hello, guys. Hello, guys.
what we can do with Diffie-Hellman and what we can't do or shouldn't do with Diffie-Hellman. So let's talk about man-in-the-middle attacks and how they're a real problem for Diffie-Hellman when it's used on its own, and that's where we bring in RSA or public key encryption to help us. What we can do with Diffie-Hellman and what we can't do or shouldn't do with Diffie-Hellman. So let's talk about... We won't go over too much of Diffie-Hellman again, right? Plenty of videos on that already. But let's remember we've got good old Alice and Bob, and we have some shared parameters already. So a generator G and a large prime number N, and they're going to share some information and calculate a shared key. So Alice is going to generate a private value A, Bob is going to generate a private value B. They're going to share, and I'm going to simplify the notation, a lot here, just so we don't spend ages writing it out. But Alice, broadly speaking, will send Bob G to the power of A, like this. So G to the power of A, and Bob will send G to the power of B, and they use that to both calculate G to the AB, all mod N. Right, so G to the AB. What this Diffie-Hellman and what we can't do or shouldn't do with Diffie-Hellman. So let's talk about man-in-the-middle attacks and how they're a real problem for Diffie-Hellman when it's used on its own, and that's where we bring in RSA or public key encryption to help us. We won't go over too much of Diffie-Hellman again, right? Plenty of videos on that already. But let's remember we've got good old Alice and Bob, and we have some shared parameters already. So a generator G and a large prime number N, and they're going to share some information and calculate a shared key. So Alice is going to generate a private value A, Bob is going to generate a private value B. They're going to share, and I'm going to simplify the notation, a lot here, just so we don't spend ages writing it out. But Alice, broadly speaking, will send Bob G to the power of A, like this. So G to the power of A, and Bob will send G to the power of B, and they use that to both calculate G to the AB, all mod N. Right, so G to the AB. What this allows us to do is share two values in public and use them to calculate with our private value something no one else can do. Right, that's really helpful. But what this doesn't do is provide any protection from someone sitting in the middle here and intercepting these messages. So let's look at a different version of this where there's someone nefarious in the middle. Let's call him Sean. So same again, Alice and Bob, and now we have Sean sitting in the middle. Now, Sean has control of this network. That's the issue, right? So you can knock man-in-the-middle attacks and how they're a real problem for Diffie-Hellman when it's used on its own, and that's where we bring in RSA or public key encryption to help us. We won't go over too much of Diffie-Hellman again, right? Plenty of videos on that already. But let's remember we've got good old Alice and Bob, and we have some shared parameters already. So a generator G and a large prime number N, and they're going to share some information and calculate a shared key. So Alice is going to generate a private value A, Bob is going to generate a private value B. They're going to share, and I'm going to simplify the notation, a lot here, just so we don't spend ages writing it out. But Alice, broadly speaking, will send Bob G to the power of A, like this. So G to the power of A, and Bob will send G. So you can hear G to the SB. What Sean...
This is G to the B.
Yeah, there's nothing in here that says this is Bob from then on. So Sean comes in here and goes, oh yes, I'm Bob, right? And he isn't. So he generates a private key S and a value G to the S and sends it back.
And as far as Alice knows, this is G to the B.
Yeah, there's nothing in here that says this is particularly Sean. Bob could have generated the same, we're calling it S, but it's just a number. It could have been generated by anyone. So he sends this back, they perform a normal key exchange, and they end up with G to the AS. So Sean has now an established shared secret with Alice. Right, so far, so good. Now, Sean then knows that Alice wanted to talk to Bob originally. So then Sean says, my name's Alice, can I establish a shared secret with you? So Sean sends G to the S over to Bob. And Bob goes, oh, brilliant, and sends off G to the B back to Sean. And they establish a shared secret, G to the SB, or BS, or, whatever, right? G to the SB. What Sean has done by sticking himself in the middle here is calculate two different keys, both of which he knows, and he can then use them to intercept every single message sent between Alice and Bob. So Alice then sends some actual HTTP traffic or something like this, encrypted with a key derived from this. Sean can immediately decrypt it, re-encrypt it with SB, send it off to Bob, and essentially act as a man in the middle at every step. So every time a message is sent, decrypt it, read it, do whatever you want, change it, re-encrypt it and send it on. Right? This is a huge problem because Diffie-Hellman provides no way of stopping this. Right? That's not what it's designed for. It's designed for two parties, I suppose, that trust each other to generate a shared secret. If you start throwing other people into it, the whole thing breaks. This is where RSA and other public key cryptographic schemes come in and rescue us.
To me, straight away, Diffie-Hellman is dead in the water, right?
Right, Diffie-Hellman's in real trouble here. But luckily, it isn't the only public key protocol we've got. So this is what RSA does. Let's imagine that Bob is a server. So he has a public key and a private key associated, let's say RSA or DSA, it's not important. So we have Alice and Bob again. I'm going to get tired of naming these. I should have just put A and B. Bob has a private key and a public key. So remember that, back to the video that Rob did on public and private key and the things we discussed in the past.
Anything you encrypt with key A can only be decrypted with key B.
Like on WannaCry and so on. The public key is given out freely. It's probably on Bob's certificate. The private key he holds back. So this time, Alice wants to talk to Bob. What we want to do is ensure that no one is sitting in the middle of this conversation. Also, as it happens, we'd quite like for Bob to verify his identity because we want to make sure we trust the server, right? So we can bring that in as well. Alice sends G to the A over to Bob just as normal. We're assuming that the generator and the prime number have already been established. We're not worrying about this. Bob is going to send over G to the B, but to stop anyone from sitting in the middle, he's going to bring his private key and make sure that Alice knows that only he could have sent that message. He sends G to the B as well as a hash of this message or a digital signature of this message signed with his private key, which would be, you know, something like a hash of G to the B, that's too many brackets, and then all signed by K private.
So if he's signed it with his private key, the only thing that can decrypt that makes sense of it is his public key.
Yes, that's right. So what Alice will do is something called a signature verification. So she will take G to the B, perform the exact same process, and then apply the public key to his encrypted version and see if they match. And if they do, she knows that only he could have done that because only he has the private key. This is assuming he hasn't given the private key away. We like to make that assumption, otherwise everything breaks. What he does by sending this over is Alice still gets G to the B, like she did before, but she can combine with A to get G to the AB. But Sean or anyone else nefarious, other nefarious people are available. If they try and use a different value, they won't be able to sign it with the private key that Bob had. Right? If they can, that's a real problem. But they can't. So Bob is able to send a message to Alice that not only shares his Diffie-Hellman parameter, which is something that needs to be done anyway as part of the key exchange, but also sign it to ensure that only he could have sent that message. Now, this is a fundamental part of numerous internet key exchanges. So the IKE protocol that's used in VPNs and the handshake used in TLS, or any time you see HTTPS, this is the kind of thing you're going to see. I mean, in fact, if we go to a standard website, this is Google Chrome's security overview that is telling us what the handshake in TLS establishes as a cipher suite for our communication with this server. And you can see we're using TLS 1.2, elliptic curve Diffie-Hellman, and RSA. So we're not using Diffie-Hellman on its own. We're combining it with RSA in this kind of mechanism such that no one can be a man in the middle and intercept our messages and mechanism. Such that no one can be a man in the middle and intercept our messages and interfere with them.
It does sound like we are potentially overcomplicating this. I mean, if we've got RSA, why do we need Diffie-Hellman?
Yeah, you're right. So technically speaking, we don't. Technically speaking, we can use RSA in, let's say, a TLS handshake. And historically, that's what's been done. So what would happen in that situation is Alice Celeste would generate a shared key and encrypt it with Bob's public key, such that that way she knew only Bob could ever read that secret key, and then they'd carry on the conversation. The issue is one of something called perfect forward secrecy. So the problem is that if you did this, if you used only RSA ever to perform encryption, right, then if anyone ever breaks that RSA key or hacks into the server and obtains it, or Heartbleed turns up and gives it away, then someone who's been recording messages between the two suddenly can decrypt everything. Right? They've got all the handshakes, so they can decrypt that symmetric key every time and decrypt every single historic message that's been sent between Alice and Bob.
So Diffie-Hellman is more of a kind of per session deal, right?
Yeah, Diffie-Hellman, RSA keys are established and DSA keys are established over a long period of time, let's say 1 or 2 years. And to save us a real problem if they get broken, we don't tend to use that for the actual encryption. What we tend to do is generate something called an ephemeral Diffie-Hellman key, ephemeral meaning we do it pretty much every time, and make it bits.
We had a... Well, I want to talk to you about DSP, mainly because when I talk about audio engineering on my channel, most of my subscribers really run a mile whenever I touch any code. They kind of go, I like audio engineering, but I don't want to know about code. So I've come to a place where I hope a few lines of C might be appreciated. Do you think that'll be the case?
I'm hoping so too. I'm hoping so too.
Whether you're dealing with sound, which is the examples that I'm going to give you today, or whether you're dealing with any kind of time series data, it could be financial data, it could be temperature in another country, in a certain place, and it's important to do things to that data. And the thing that I think most people are familiar with is having a waveform and it actually producing something you can hear. Your ears are very sensitive. So all the examples I'm going to give you here, surprisingly, are going to be musically related, but this is applicable in so many other places. So the first thing I want to talk about really is equalization. Do you know what equalization is?
I remember having an equalizer on a stereo where you turn up the bass or turn down the bass.
Yeah, turn up the bass, turn up the treble, doing anything. I'm just going to play something, a drum kit through, and I'm just going to turn up the treble, turn up the bass, turn up the middle, just so that you can intuitively hear what an EQ does and what I'm talking about before we get into some code. My friend Jan played these drums. So this is just the drum kit as it would be. If I wanted to turn up the treble like you would in your car or on a hi-fi, all that all gets turned up. Or you can turn it off, make it sound really dull. The same would be true of the bass. That's distorting nicely. But you can end up with more bass there, or less bass. Sounds very thin. If you're watching on a phone, you probably can't tell any difference between those examples, but doesn't matter, imagine it in your mind. And then the mid frequencies. So audio is made up of a whole frequency spectrum with really long waveforms and really small waveforms, and they all come together with different frequencies and different amplitudes. The longer frequencies are the bass frequencies, what we would consider like the bass guitar and the bass drum, stuff like that. And then all the and all your hisses and your sibilants is right up at the top. And all the stuff that we hear really clearly sits in the middle somewhere, and that makes we want to judge industry studio to pad it in a high frequency. P is just digital signal processing. It's just maths, basically. You're just getting the points on the wave, and then we record those numbers. We've covered that in a previous video. Basically, we're taking those numbers in, and we're giving a new number out, and whatever the new number is dependent on the code that we write. So let's load a piece of software here called Plugin Doctor. So for those of you that don't know, I work within a thing called a DAW, or a DAW, a digital audio workstation that allows you to have lots of tracks of audio. And then while I've got all this nice stuff behind me that's real physical pieces of equipment that you can plug in to do audio, you can also have digital equivalents to that. You have plugins that you can put over things. So if you want something to have a reverb, sound like it's in a massive room, or you want to distort something, there's a plugin to do kind of anything you want. And at a fundamental level, all it's really doing is taking the sample number and changing it somehow and overwriting the place in memory where the last the last sample was, so that it changed it somehow. And digital plugins are trying to mimic, a lot of the time, they're just trying to mimic what's on the outside here. Now, there's a great plugin, one of my favorite plugins of all time, which is called Formula VST. VST stands for Virtual Split Up Oscilloscope, to some sort of notepad or VS Code type window. Due to my age and eyesight, I'm going to up the text size there. But as you can see, it just has a function called Formula Main, which basically sets the output to the input and then returns the output. This is just C. So this plugin here is doing absolutely nothing. On Plugin Doctor, if I separate those two so you can see them both on the screen, you can see I've got a -6 dB signal going in.
So that's just the volume effect.
That's just the volume of what's called a Dirac spike. So it's just a single one sample in a sea of zeros. It's the way you do impulse responses. You send it a single spike, and then whatever happens to that will draw a waveform. And at the moment, it's doing nothing whatsoever. So if we were to put an EQ in here, like that Pro Q4, so I'll load that up. So you can see, as I change things on the EQ, it's also showing me in Plugin Doctor what it's doing. So it's a really nice way when we're hearing it. I'm doing 4 by hour. So I'm going to set that to 0. And then basically lost. We just average. We've lost some treble.
Oh, so the highest frequency.
But that. A lot of top end there. And if we done, if I bring that, we would do a Blue Peter. This is one that
is actually generated. Specifically, Ethereum uses this one. I always forget how to pronounce it. And Sol use ED25519 as the elliptic curve, which basically means it's a curve like this. And whenever you generate a public-private key, some point on that curve, which is, a curve can technically, effectively have infinite number of points. So whenever you generate a random public-private key, आप उस curve पे कहीं lie करते हो, and that translates to a public and a private key for you. And that is why the probability of two people having the same public-private key, if they generate it randomly, is very low. Because अगर एक curve है जिसपे infinite points हैं, if you take two random points on it, very low probability you and I both, lie on the same point. To recap, whenever you want to eventually, buy BTC or receive BTC from a friend, you will have to generate a public-private key pair. In case you want to get BTC from a friend, you will use this encryption algorithm. If you want to get Solana from a friend, you will use this encryption algorithm. Generally, you will not write code. You will, open a wallet like this and, generate a wallet. So, मैंने भी मान लो यही किया. I went to Soulflare, added this, clicked on the generate button, it generated a public-private key pair for me. That exists here locally in this, wallet of mine. And I told a friend to send me $9,000. He sent me $9,000. If I want to ever send money to other people, when I click on send, when I select that amount and that address, when I click on send over here, I'm actually signing a transaction and sending it to the blockchain. So the blockchain can indeed verify Harkirat, who owns the private key of this, has sent this message. There are a few other use cases of public key cryptography. Whenever you SSH into a machine, whenever you've tried to push GitHub via SSH, if you've tried to push to GitHub via, whatever, there are, two URLs that you might have seen over here, an HTTPS URL and an SSH URL. If you use an SSH URL, you might have created a key pair on your machine. If I open my terminal, you can always run this command called SSH-keygem. And when you run this command, it generates a public-private key pair on the ED25519 curve. कौन सा curve था ये? Solana वाला. So if you want to generate a Solana public-private key pair, you can actually use this command also. This will dump a public key and a private key in your, machine at this folder. So if you look at my.ssh folder, notice there is an idrsa.pub, idrsa. These are the public-private key pairs that I generated years ago, back when I was in college, using the RSA algorithm. Today, generally, you generate public-private key pairs using ED25519. It's a little more secure. ठीक है? Why am I still using my old college key? Because my private key, my public key has been in GitHub for years. So if I want to ever push that public key already exists in GitHub on my AWS, so if I do change it using this, fancy algorithm, then I will unfortunately have to, But just 1 second. I will have to change it in GitHub and AWS everywhere. I will take a 1 second break. Someone's knocking on my door. Apologies. What was I saying? Public-private key pairs. You can generate one yourself. This is the curve that Solana uses, and this is the default one that comes in this SSH keygen command now. Back in 2015, when I was in college, the default public key, private key that I generated using RSA. This was this very first algorithm over here. Let's do a poll. Do we understand asymmetric encryption? Because actually one more thing before we do a poll, which is, let's look at the various ways of creating public-private key pairs, signing messages and verifying them. Number 1, create a public-private key pair. Number 2, define a message to sign. Number 3, convert them. Blah, blah, blah. Ignore this slide. This is more of when we code is when we will see the slide. Ignore the slide for now. Abhi ke liye, do we understand everything until asymmetric encryption? Can we get into Bitcoin and how it works? And where does it use these concepts of public-private cryptography and asymmetric encryption and AD25519 curves, and how does BTC work, and how the white paper at least stated that it works. Okay, we're at 88%. I will do a very small 1 minute, 2 minute Q&A to make sure it reaches 91%, and then I am happy to proceed. Since every message is signed by my private key, can I somehow decipher it at the end? And at the end rate, so you can't decipher it. That's the whole property of encryption, unless of course you have a quantum machine like you mentioned. At the end, quantum machines are growing. It might be very easy for anyone to do it. Yes, which is why people are now creating quantum resistant, or there are discussions around making BTC, Ethereum quantum resistant, which means everyone's public-private key pairs would probably translate to something else. So yes, if nothing changes, then in 20 years, everyone will own everyone else's Solana, Ethereum, because computers will become so good at finding every public-private key out there. But abhi ke liye, it's computationally infeasible to find all public-private keys, or randomly get one that already has Solana in it. How bridging happens in crypto, whole different topic. Probably not a good discussion for today. But if you want to bridge from one chain to another, the way it happens is it gets logged on one chain, it gets minted on another chain. Specifically for USDC, if you use CCPT, Circles Transfer Protocol, or something like that, CCTP, Circles Cross-Chain Transfer Protocol, then because Circle owns the mint on Ethereum, Solana, Aptos, it can just burn it on one side and mint it on the other side. If you use something like Wormhole, then it happens a whole different way of locking tokens on one side and minting some random token on the other side that you swap for USDC. There are various types of bridges that exist, but not a discussion for today. How the value of cryptocurrency is decided based on trust and confidence of people, or is there any metric to decide the value of crypto? If it is based on trust and confidence of people who missed the chance to buy BTC and can start a new crypto, they can get benefit. Wow, beautiful. The question is, why can I not create a new cryptocurrency and ask everyone to, trust it, and we can all create a new Bitcoin, and then we will all own the new Bitcoin because we missed the old Bitcoin train. And the answer is yes, you can do that. Generally, current blockchains are gain value based on कि team इतनी पुरानी है, these are the features that this blockchain has, and this is what it introduces. For example, BTC, even though it's a very unoptimal and slow and computationally very expensive blockchain, still holds value because it's the oldest one. So it's you can create multiple blockchains, but they will not making people believe, okay, this will probably be the store of value. It takes time, which is what BTC and Ethereum have, and your coin might not. After sending data goes to the RPC first, then to the miner. What are RPC checks? And is sending coin means I am giving ownership to this coin to someone, to this user? A bunch of questions in there. After you send someone a coin, there are two types of coins you can send someone, either Solana or a custom token like a USDC or a Trump coin. you do send it to an RPC, which does forward it to a real validator in the end. RPC checks are if you're trying to do something, that for a fact is going to fail. An RPC can simulate your transaction and see क्या आप जो करने की कोशिश कर रहे हो तो हो ही नहीं सकती. For example, you might be trying to do something when you have no Solana in it, in your wallet. So it doesn't make sense to forward the request, which are what are RPC checks. When you do say I've given my tokens to someone else, technically it means very different things on very separate blockchains. In case of Solana, it means they have that other user now has an associated token account in which a number exists. So if I've given them 100 USDC, the 100 number exists over there, and then in my associated token account, it goes down by 100. If you're sending someone Solana, that means उस public key में जो data present है, उस data में my amount has gone down by 1, their amount has gone up by 1, and so on and so forth. Different blockchains pay. Technically, it means a different thing, but yes, overall it means that the ownership of the coin has transferred. Can you explain why we need encodings and what are the use cases? Yeah. So, okay, a simple example is when you generate a public-private key pair, जो algorithms हैं RSA or whatever these algorithms are, they don't have a concept of encoding. They're just generating bytes. Their papers are written कि यार एक public key बनेगी ऐसे bytes में, एक private key बनेगी that will have some bytes in it. The public key might be 32 bytes. The private key might be 64 bytes. You and I can't share bytes with each other, right? If my public key was a bunch of bytes, then I would have to copy a bunch of zeros and ones and send it to you. And you would then, paste those zeros and ones somewhere and then, send money there. Which is also totally possible. In the end, when I copy my public key, it is actually converted to zeros and ones and, and then whatever, the Solana is increased or decreased. But for humans, it's really hard to understand, which is why any byte array is much better represented in hexadecimal in base 58. Right? Light has gone. अरे यो क्या हो गया? Hello. So the Wi-Fi stopped working. I am on mobile data right now. So I would like to check if you guys can hear me and see me before I proceed. Can you guys hear me and see me? It is laggy. All right, lagging a bit. We will take a small pause. We will just have a random conversation. Is there any database used in blockchains? Unfortunately not. Most blockchains have to move really fast and most of them store most data in memory. And that is why, you don't have a concept of databases. How string of numbers will be stored in binary like this? Well, again, it depends on mota uski encoding kya hai. Generally, strings are stored in ASCII. So even if it's a string of numbers, it will still be stored in ASCII. That is exactly why they say in JavaScript, if you have to store a very big number, then store it in the form of string. If you have a very big number that you want to store, then you should store it in the form of string, because this string eventually is encoded in ASCII. Am I sharing my screen? I'm not. But if I do share my screen, this string is actually converted to ASCII. But if you are storing a very big number, then most numbers are either 32 bits or 64 bits, and hence you will run out of whatever space and not be able to store it. it still stores over here. JavaScript does some hacks over here, but I'm sure if it's a very big number, you have to use something else like bigint. Let's see if that's true. Yeah, it's just stored it, but does it actually store all the information in there is the question. For example, it's storing this. Yeah, it's probably not storing every number. Do you get it? I wanted to store a very big number. I couldn't store it in an int variable. I could only store, this much precision into 10 is per, into whatever, 10 is per 300. But if I do store, this very big number in the form of a string, I can. What does that tell you? That tells you, okay, even if you have a very big number or a small number, but if it's stored like this in a string, it's actually stored in ASCII and not stored as normal decimals. I'm sure it's still a little laggy, which is why I am just answering questions until the Wi-Fi comes back, and then I will move on to, more stuff. So I'm going to stop screen share, and if you have any questions, I'm happy to answer until the Wi-Fi comes back. The long chain of data are moved in all system for checks. I don't understand that question, Himanshu. I want to learn about bridging, where you study and what are the resources and check for it. You can go through the architecture. Code 3 had random videos with snippets where someone asked a question and I explained bridging. And there is you'll have to find it. I think his name, Super31, had a student called OX Naresh or something who created a bridging contract, which is what I discussed in a few classes. So yeah, just read through the architecture, that's probably the best place. We can introduce a class eventually on bridging. I've seen libraries that convert data content from some files to another, to base64 string. Can you shed some more light on it? Converts content from files like PDF to base64 string. I don't know why, I understand converting from PDF to Word. I don't know why you would want to convert a PDF to hex. I'm sure there's a specific use case that I don't know of yet. Apart from financial use cases, what are some of the other real-world use cases of Web3? Unfortunately, not many. People are trying decentralized physical infrastructure networks, which basically means incentivizing someone for owning hardware. People are trying, a lot of things. People are trying RWAs or real-world assets, which somewhere or the other lie in finance. 99% of the use cases, real use cases right now, unfortunately, are only in finance. 9% of assets, which somewhere or the lot of things. People are trying RWAs or real world assets.